Good afternoon, everyone, or good evening, or good morning, depending on your location in the world. Today I'll be talking about failure analysis for our industry, electronic systems, using ion chromatography and ion chromatography mass spec. I've been running ion chromatography systems since 1986, and have used thermal systems consistently, but have worked with other systems and found a lot of interest in the industry, in our electronics industry, in using tools that allow us to quantify and speciate the different ionic and organic residues. Today we'll be talking about 3 different case studies using both IC and IC mass spec to look at and see how we can extend or understand the effects of the process. We'll talk about technology changes in the electronics industry from the mid-80s to today. We'll look at a definition of cleanliness. We'll talk about traditional testing, historical industry tools and monitoring techniques, new tools, and we'll look at these 3 case studies that we talked about. And then we'll talk about some of the elements that we find are better designed for understanding reliability impacts and reliability risk ahead of putting a piece of hardware in the field. In the electronics industry, a lot has changed. Not only have we changed from a leaded to a lead-free soldering world, which changes the soldering temperatures, but we've changed the realm of cleaning and not cleaning. And historically, the industry, up until 1991, cleaned 100% of the circuit boards that were manufactured for high reliability hardware. Everything was cleaned in either Freon or 1,1,1-trichloroethane. We had a lot of historical data with high solids, raws, and fluxes, using tools that allowed us to create a good solder joint with a wave solder process and some early solder paste and reflow conditions. But after the Clean Air Act came in 1987, the industry started moving and transitioning between 1990 and 1992 to everything that was new. It was a huge disruption in the technology. So a lot of people went to no clean, so we didn't have to invest in new cleaning systems. So no clean fluxes, low solids, no rosin, that weren't solvent cleaned, that were allowed to leave residues on the board and have a insulated protective residue was the marketing term. The reality behind those no clean flux residues meant that you had to have good clean hardware coming in, good clean boards, good clean components, and fully heat activate the flux so that it was benign. Since 1991, we started our company in 92. We found that there's a lot of dirty incoming boards, dirty components, dirty flux application issues that have created a huge shift in reliability issues. The other issue is cleanliness monitoring. We've been using traditional tools for monitoring the cleanliness of a circuit board, which is just pouring some alcohol and water over the surface of an assembly or a bare board, and then we would measure the resistivity change before and after. So looking at that delta, then using a very complex calculation and algorithm, we would come up with a function of, is this clean or dirty? But it never correlated to reliability or predictability of the field performance. It just was a general gauge to say, was the system cleaning as well as it did before, again, using solvent systems with raws and fluxes. So a lot of things have changed in our industry. we have seen shifts, we'll come back to that one, in the technology. Here's a 1991 rosin flux photo on the left of a telecommunication router board. And then on the right, we have a server, just a small section of a server board where it was all built with no clean fluxes in 2017. Very similar to what we're seeing today. This board was probably 12 layers compared to the 24 layers that we're doing today. The board on the left was probably 3 or 4 layers, probably a 4-layer board at best, and it didn't need to be that complex or that complicated. So there's a huge difference in component spacing and component architecture and entrapment issues and the size of the components. We reduce the size of the components so we have more places for flux to be trapped, but we also have a smaller space for reactions to occur between anode and cathode and set up a corrosion cell. And we'll be talking about electrochemical migration, dendritic growth, which are the same thing, parasitic leakage, and the events that cause reliability issues to have traces corrode open and then grow dendrites through or from that open copper. The issues of cleanliness as they impact reliability, typically the relationship between the amount of surface contamination and the probability of electrochemical migration has always been understood, but never well quantified. And when I first started doing ion chromatography, I was very shocked to see our industry was not able to quantify chloride or sulfur or sodium residues from a manufacturing process on a circuit board. And to look at it as an overall cleanliness of this whole circuit board itself, we would take and assess the effect of where the contamination was coming from. And in many cases in today's hardware, we see 2 or 3 locations that will have a dendrite short, as we see here on this area where the dendrite basically came from contamination that was trapped in the via and migrated out due to the unreacted flux that was trapped in the via from the bottom side soldering, wave soldering operation. So taking a look at knowing these levels of contamination, understanding what their effect is on a localized level doesn't correlate or didn't correlate historically to the amount of predictable reliability. In traditional tools, again, we used what's called a ROSE method, resistivity of solvent extract, poured alcohol water at room temperature over the surface of the board, collected it, and then dropped it into some magical algorithm and said, okay, here's what the effect of the residues are, and here's how we can understand what that value means. When we shifted to no cleans and water-soluble fluxes in the 90s, all those relationships and all that historical data really did not translate, and we didn't get good correlation to those types of tools, even though the IPC and the industry still accepted them. But they were the only tool that was available in that time frame, and so everybody was still trying to figure out how to make it work with the new fluxes and new technology. This little image here shows where flux residues underneath a connector that passed the ROSE test were high enough to absorb moisture and set up a corrosion cell on a 200-volt input, where the connector would actually set up and corrode dendrite underneath and then catch the connector on fire and cause these units to fail in the field in a relatively short period of time, within 2 hours. Most people think about cleanliness as a general term, and it's really ambiguous in our industry. So we are trying to develop better understanding of how the issue of cleanliness is directly related to reliability. And if you've got enough moisture, if you've got enough voltage differential, and if you've got enough corrosive residue, you've got the right recipe for creating a dendrite, or creating a condition where the failure is actually going to occur, but it's always in a localized area. So we've taken the approach to isolate and extract residues from specific areas with a steam approach. We've developed and had a tool for the last 20 years on the market for process monitoring and failure analysis to assess what those residues are and how we can look at them, and comparing them to traditional ROS or surface insulation resistance type measurements. They're completely different. These are general average, both electrical or chemical assessments. When I developed and published the first ion chromatography test method for the IPC back in 1994, we were doing bag extractions of the total board trying to correlate to that ROS test. Again, using isopropanol alcohol at 75%, DI water at 25%, letting it soak for an hour at 80 degrees C, just so we could get 95% of the ionics that were extractable off in the first hour. And then when we did the second extraction and third extraction and fourth extraction, we got less from that surface. So we would look at the original analysis and start saying, okay, with rosin fluxes, we could get a really good reaction and see what the fluxes were and see what things were doing, but we didn't have any real big problems in the 80s. When we started switching to no cleans and started switching away from rosin-based fluxes, we started seeing great numbers of reliability recalls and failures with dendrite growth and corrosion issues and parasitic leakage issues, and we knew that we had to go and look at things with a better tool and a better approach. Taking the technology that changed, and again, I know for this audience, you're not as aware of some of the technology issues that we can get into the details of, but no clean fluxes, lead-free solders, the development of QFNs and micro BGAs and flip chip packages and bottom terminated components, all of those structural changes created new and more impactful entrapment areas with extremely high levels of sensitivity. So now we have a very sensitive device with a critical opportunity for trapping residues underneath that device, and we had really no good tool to process, monitor, or assess what was going on from that step of the process. And so if we change everything in manufacturing and technology and we don't change the way we monitor things and we see more failures, that means our monitors are not working, our process understanding is not where it needs to be. And even with the basic ion chromatography, we knew that we were not seeing some of the things that we could see that would help us understand why we were seeing some dendritic growth or parasitic leakage in things that had low levels of chloride. And typically the primary corrosion mechanism was one of the halides, either fluoride, chloride, bromine, with an amine structure. So we would have an amine hydrochloride flux activator from a Hassel process that would be left on with a polyglycol carrier. Those are very moisture absorbing residues, and if they're not properly rinsed on a bare board from a Hassel process step, they get to be very good failures very quickly. But with components trapping these fluxes where they're not allowing them to transition in temperature because they're so tight to the board surface, we see the effect of the residue and as its impact on performance, growing these dendrites and shorting underneath the package itself, even though everything else on the board is fully functional and performs great. We talk about about contamination and residues, and this is a short list, kind of an overview of each step of the manufacturing process, and a no-clean assembly creates a chemical signature. And from a failure analysis lab standpoint, I need to understand and have analytical tools to understand what kind of plating chemistries are we dealing with, what kind of organics are we getting and dealing with, what are the etchants and the water quality issues. Some of the best circuit boards have come out of some places that use DI water, ultra-pure DI water, throughout the manufacturing process. Some of the worst places that produce circuit boards come out of places that are using tap water or even Chicago River water or Penang River water to rinse those boards. And even when we have good DI water as a primary source, a lot of these board fabricators will use a cascade forward system where they have 3 tanks or 4 tanks of dirtier levels of water that they'll just recirculate and use to knock off the initial level of contamination, not realizing that these things will build up a lot of contamination very quickly, and now we're just puking more contamination on the boards, creating a whole other set of problems. So board fabrication, component fabrication, plating issues, fluxes, as we've said, cleaning processes. There's still about 25% of the industry that cleans circuit board assemblies for high reliability hardware, and we are seeing more and more people move to that because of the high reliability issues. We have a lot of conformal coatings that are trapping residues, or the monomers are reacting with the flux residues that are there, setting up corrosion cells underneath the sample itself. Staking compounds, outgassing issues, temporary maskants, and then the enclosures, the hardware that we put the electronics in, the plastics, the vibration dampening foams, all those things have a tendency to outgas. We'll outgas sulfur, we'll outgas chlorine, we'll outgas acetate, and those things also set up corrosion cells. Those chemicals, so understanding what those elements are, really allow us to be able to come back in, use a localized extraction, see the corrosion site, and come in and say, okay, this residue came from this step in the process. And we go back to that process or that material, and we can then make that change, remove that from the product, bring in new product or new materials or new processes that are cleaner, and be able to improve that process. And that's how we've been successful for the last 29 years. Moving on. Cleanliness assessment, what is the circuit board cleanliness, and how do we assess it, and how do we know what the difference is between good and bad? It all boils down to understanding what level of contamination is present to set up that corrosion cell. So using tools that we've developed, we can actually create an electrical response to see what causes the conditions for dendritic growth. Doing failure analysis for so long, we've been able to go in, analyze these types of failures where the dendrite that caused the short of the hardware, and this is a part has been removed from this called a QFN, and it had a dendrite grow in a fielded application and cause these things to short on an automotive application. And we found that this level of contamination of the weak organic acids were extremely high, were not properly heat activated, and set up that corrosion cell. The same with this other dendrite growing underneath this hazy material, which is the conformal coating. We were able to see the reaction between the monomer and the coating from the coating react with the flux residues that were not fully heat activated. Now we have weak organic acids, succinic and adipic and malic in this case, set up a corrosion cell and grew dendrites within 24 hours of going into the field with a gas meter system. So it's learning how and understanding these types of systems. We create tools, I'm not sure why my picture got moved. We create tools to look at where these contamination issues are, we bring the steam down through this test cell on the C3 head. We let it soak for 20 seconds, and then we aspirate it off the board surface, put an electrode that's sacrificial in that solution. We collect 2.2 mils of solution with 250 microliter cycles of extraction solution, which is ultra-pure DI water that shows less than typically 1 ppb or 5 ppb of any anion or cation that we can detect. And so when we introduce this to the surface at 175 degrees Fahrenheit, typically by the time it goes through the system, it starts out as steam and ends up as a very, very hot steam aliquot or dispensed hot water. We let it soak for 20 seconds, we aspirate it off, and then we collect it. 2.2 mils sit in this collection reservoir. We apply a 10-volt bias, and we see how long that takes for it to function. So with the C3, we're able to isolate those areas and then see what those reactions are. When we take a look at the effect, now we're monitoring the corrosivity of that solution. We're monitoring how much microamps of current leakage we see between that 50 mil spaced gap electrode, and we can look at the effect of how the time interval and the reaction, and we've chosen 250 microamps of current for a event. So we know that we can see dendrites growing and shorting at 250 microamps. So the faster that occurs, the greater level that we have as contamination. The longer it takes, the cleaner it is. So we've been able to establish between 120 seconds and 180 seconds that the good DI water will have a good clean run, and we define it as clean, and anything that's less than 120 seconds is considered dirty. So we look at those kinds of residues, and we've come up with a corrosivity index where you can actually just plot your values based on the current divided by time. So we can see what that reading is. We all know what ion chromatography and how wonderful the system is, but it has its limitations. And that's been one of the struggles that I've had trying to deal with just conductivity. And I've tried a variety of analytical systems to quantify and speciate and separate out. And I get coelution issues with methane sulfonic acid and formate. I get coelution issues with sulfate and some of the organic acids. Everyone was surprised when we started reporting that we could see the organic acids, succinic, malic, adipic, on the AS22 column. And we have a 17-minute run with an isocratic system with a bicarb carbonate eluent. We're able to see those very effectively and get a good run in our system. But it wasn't until we introduced ion chromatography mass spec into our system where we ran a separate IC system and a separate mass spec away from our standard ICS 3000 and 5000 system. And we were really surprised to see that we could see chlorate, chloride. We could look at some of the other elements and get better separation and great separation between the organic acids. And with 29 channels, we're seeing 19 of those as organic acids. And we've got 10 set up for just the primary anions. And we've been really developing and using this technique, and a lot of companies are really glad that we're able to now speciate and look at ratios of fluxes and say, okay, now I can tell the difference between a surface mount solder paste flux that's been fully heat activated versus one that's been partially heat activated, looking at a pen and paste process where they reflow the top side of the board and the solder paste runs down the hole, the through hole, and ends up with flux on the bottom side of the board. Well, the flux on the top side that saw all the primary reflow heat is good and benign and protective, and the stuff that's on the bottom side of the board is not as fully heated and is very moisture absorbing and has set up corrosion cells. So we can look at that partial degradation of that flux and see the reaction and ratio differences of extractable residues. So using the C3 and steam extraction, we're able to go in and look at and understand, okay, why do we see dendrites growing here versus why don't we see things here? And we can see certain ratios and see the fact that some of those degradation products are not present in the good areas, and some of the degradation products and some of their byproducts that they're coming from these reactions are still very reactive in the bottom side. So we can see those kind of differences and see how that affects the performance as it relates. Again, our standard IC mass spec with the auto sampler, wonderful tool. It's a 40-minute run versus a 17-minute run, so we don't run 100% of everything we do because we do have 2 IC systems running usually 20 to 24 hours a day with a couple hundred analysis. So we do see a lot of systems. We probably run more IC analysis than a lot of labs around the world. What we can see between the IC mass spec and what we see with just IC, looking at the primary anions, and just looking at that. And our system is only set up for IC mass spec is only set up for anions. We don't have a cation side of that, so looking for that as well. I want to see what else I'm not seeing. But these are some of the organic acids that we deal with, and some of the things that will collude with certain elements. And right now we try to dial everything in, so a lot of these organic acids will come out as a colluting element with succinate or succinic acid, and we'll just have a single value for that peak based on succinic acid. It creates the condition, at least allows us to say, historically, where are we at with a water extraction on that sample? And then we can go and speciate it and look. But we've set limits as to what level is good and what level is bad based on the weak organic acids, and have found that for a surface mount process, 25 micrograms per square inch of weak organic acid, which is the collective of all the different organic acids from the different fluxing processes, we can see that on the surface. And anything that's above 150 micrograms per square inch from a waste-solder process is considered to be corrosive and conductive as well. And that has some variability, but those seem to have played out very well historically. We talked about ion chromatography as a failure analysis tool. And one of the cases that we've had to work repeatedly over the years is, let's take a burnt board, figure out what happened to it, compare it to a current production board, and see what's different between the current production and the failed board, and see if there's any similarities. And using both the IC and the IC mass spec, we're able to see certain key changes. So if we look at the data from the bare board, and this is all in micrograms per square inch, so what we've done is we've taken the part per billion or part per million level output from the IC, and we have taken the volume extraction in the surface area, which is 2.2 mils of DI water and 0.1 square inch area, and be able to convert that into a micrograms per square inch ratio to look at that as a normalizing effect over larger, or comparative to larger areas. The failure, we saw high levels of bromine, which is typical for a board that has been burnt. The bromine is a flame retardant built into the system. It's designed to help minimize the thermal events, and so we see high levels outgassing from a board that has had some thermal event. But what we typically don't see are high levels of weak organic acid. So looking at what these weak organic acids are, will help us understand, and we compare that to the good board, the current production board, where they had levels that were, less than 25, where the sodium levels were high as well. So if we look at the touch-up repair flux that they used, it was high in weak organic acids and high in sodium as well. It showed dirty in the C3. just like the samples from the failure. So what we believed happened is that there was a localized rework area nearby, and it was brush cleaned into this area and set up a corrosion cell on a very critical part of the circuit within 3 or 4 seconds. After this unit was powered up, it blew the capacitor right off the board surface. So looking at the IC mass spec data and taking a look at, and this is just this should be 19 channels of the 29 that we see. So I wanted to kind of make it so it wasn't such as bad of an eye chart. We do see other things here. A lot of them were zeros. But what we find is that the touch-up flux had malonate, succinate, glutarate, adipate as the primary activators in the flux. And the activators of the flux are there just to chemically remove the oxide issues to allow the solder to flow and wet. So you have to have an acid that's capable of reacting under temperature and remove the oxides and not create another set of oxide issues. So it's a balance, but you still have to have a strong acid. So we saw the same thing on the board surface where the glutarate, the succinate, the adipate, which is very corrosive, and the malate. So we didn't see any of the other organics that were actually present in the solder paste. So again, there was enough removal and volatilization that it just burnt off the rest of these organic acids. Again, the same high bromine issues, and we still see acetate in those areas, and that also is present in the flux, touch-up flux. So taking the IC mass spec allows us to put a better, more detailed analysis and understand what the flux residues are, where they came from, and where do we go back in the process to say, okay, let's find a way to eliminate or remove that step of the process that's causing the problem. So you can see that the capacitor that was there is a big glob of thermal melted mess. And it's due to the rework flux that was on a nearby part out of frame that was brush cleaned and had been brushed into this area. And this primary pin here is the primary power pin coming into the device to set up this functional unit to work. Case study number 2, looking at an automotive environment, we have a wonderful shorting event that occurred on the surface, and it was not well understood as to what could be causing these issues, and a lot of people were blaming flux. For those of you that are aware, these are mechanical inserted pin and pay, or compliant pin connections. So there's no flux, there's no solder in these joints. So there would not have been any reason for flux to have been isolated in this particular area. So we asked them to send us the enclosure and the housing just because we got a circuit board with a burnt area. A lot of times we'll just get the circuit board and not the whole conditions or the housing enclosure. So once we got that, we were able to take a look at everything, and we found that the outside enclosure had a thermal vent, and in there was basically it's a fiber vent. It's a little vent that keeps the moisture out and supposed to keep all the conditions so that there's a pressure relief. But this is the outside of the housing used, and you can see that there's a lot of very discoloration, a lot of visible debris and residue on the surface compared to the inside surface, but there was still some very conductive residues that were present. And when we looked at it with IC mass spec, we found that there was no flux in that residue, but there was very high levels of chloride and acetate and sulfate. So taking a look at that, it was, again, an outside salt that was deposited on the board surface that was directly in relationship to the area we're looking at. So taking a look at these case studies, we've actually found that there's a lot of issues that impact localized cleanliness. These are a number of the key areas that react from the manufacturing process and from the environmental conditions itself. We have to deal with, as electronic reliability is now one of the biggest items of failure analysis and return for many of the OEMs these days. The reliability effect is usually a very large line item in their annual liability effects. So when they have to pay out money for recalls and pay out money for repair and completely redoing or replacing hardware, it's becoming a much greater cost burden. We're finding that today's electronics are seeing more recalls due to both mechanical and chemical issues than any time in history. So we're trying to help people understand their manufacturing process, because we're outsourcing things from what used to be done in-house with one primary manufacturer to 3 or 4 or 5 levels of different subcontractors. So we try to move beyond where things are. When we look at electronic reliability and hardware performance, we're trying to see the differences of where the technology is and where the changes in process are. Process variation and process variability are key things that a lot of systems, since we haven't had the ability to monitor the process adequately, have escaped us. And traditional tools are not able to see the system's effect. Rose testing gives you a gross single number for a whole board. Bag extractions of circuit boards for ion chromatography give you a single value for a specific ion, and it kind of gives you, here's where we're at, but it's a general average over the entire board. And instead of using 2.2 mils of extraction solution, we're using 300 mils. And so now we take that 300 mils and we inject 25 microliters into an IC system, and you get a very low level of sensitivity. Part of the reason we've done a localized extraction with a very focused small spot area is to understand how to minimize that variability. So I want the greatest reaction to occur in that 25, and we push 100 microliter injection loops for all of our systems just because we want to have a greater level of response. We don't need to have high alcohol content columns. We don't need to have columns that will give us sensitivity to just weird, very aggressive organics. But what we do need to have are columns that are stable and have a low baseline that give us an understanding of how we can see very low changes or different levels of sensitivity of near eluting materials. So for acetate, formate, fluoride, the methanesulfonic acid, I need to be able to see separation there, but I also need to be able to know when I've got a swamping large peak, if I've got a gross concentration of sulfuric acid from a outgassing material or from an etchant, it's going to swamp over and see other things, so I need to be able to dilute it but still not lose the sensitivity of what I'm looking for on the other side, so on the load level detection. But we are able to see the effects of manufacturing processes, and flux vendors are changing fluxes and the activators that are in fluxes because we're changing all the solder alloys. So we need something that's more stable instead of at 184 degrees C for a tin lead alloy, which rosin was wonderful at, to 240 degrees for a tin lead, bismuth, palladium, next generation alloy that's going to see a higher temperature reflow, that's going to see multiple soldering steps on that same board. So we need to be able to have fluxes that will volatilize off the primary corrosive residues and leave behind a insulated protective barrier, which creates a whole other set of problems. So as I'm going through the reflow process, I volatilize off these corrosive parts of the flux that I don't want on the board, and they condense on larger, taller components or secondary boards that are in a vertical state. It's understanding where those residues are coming from and how those residues are going to impact reliability is another thing that we've been working on. So electronic manufacturing allows us to see the assembly techniques, and chromatography and chromatography mass spec have allowed us to see the chemical underpinnings of all those manufacturing processes, and now we can include the outside organic and elemental residues that have an impact on performance, and we see where we're working from there. So looking at column technology, looking at where we need system support is better understanding of how to quantify and speciate not only the individual organic analysis, but when we take and blend a lot of the fluxes, and a lot of the fluxes will have 3 or 5 organic acids. When they do that, you know, what are the degradation states of these blended fluxes, and that have gone through partial thermal heating and activation or full thermal heating and activation, so that they've gone through a reflow oven 2 or 3 times, and now we've got material that has seen 240 degrees dwells for 20 to 40 seconds as a peak liquidus phase, but we've ramped up from 25 C to steady states at 150 to 180 degrees C. And now we're thermally breaking down and releasing those chemicals. It's understanding what these chemicals are in their various stages and how they are able to react and pull moisture in, set up corrosion cells or parasitic leakage issues is the largest thing that we have to deal with on a daily basis. And with that, I have going to open it up for questions.
Thank you, Terry. This is tremendously exciting. What column, anion column currently using? You did mention about, I believe, AS22 carbonate bicarbonate. Have you switched already to the REG technology? And if yes, what column are you currently using for your various inorganic anion analysis, as well as organic acids, I suppose?
Right. For the IS3000 or the ICS 3000s, we're running the AS22 column for anions and the CS12A for the cations with a 17-minute run using bicarb carbonate. I found a bicarb is much more stable dealing with the flux residues than the gradient processes. And again, because I'm running a few hundred analysis a day on 2 systems, I need the shortest run time that I possibly can get, but still have the separation and capability, you know, on seeing things in the 5 ppm level and lower effectively. With the IC mass spec, we're running I think it's the AS17, but I'll have to double check.
For your ICMS column, let's presume for a second that's AS17. So do you think it would be a benefit to you if there is a column which can do really wide range of inorganic anions as well as organic acid anions, and if yes, what sort of analysis time would you think it would be acceptable from your point of view?
Very good question. One of the things that we're constantly fighting is the need to push samples through, but still get the most information. The 40-minute run that we're currently doing for IC mass spec is the longest I feel like I can run. We're constantly looking at and trying to understand how can we shorten that to 30 minutes. I think a 30-minute column, if I could get the separation that I needed in 30 minutes and understanding where those complex structures are, we could get a lot more hardware processed through the system. You know, I have the Inorganic Ventures organic acid standards, but I struggle with, are the same kind of organic acids in the modified state from the flux vendors the same, you know, and how similar are we running? And I'm trying to get, we've got good relationships with some of the flux vendors, and they've given us some unknowns, and we've run about 65% accuracy on what we report versus what they say they put in the material. But again, there's so many trade secrets. These guys won't even tell their own mother what's in the fluxes. So, you know, we've asked them to make up something similar that we can thermally degrade, and the IC mass spec has been accurate about 65 to 70% of the time on the primary activators. The succinic and the dipic are easy. It's the lactic and the glutaric and the what's the other one? We've got the malate and maleic that are starting to show up more and more because they're more stable at higher temperatures. And that's the thing that keeps changing, is different vendors are doing different things for different higher temperatures or metal alloy construction, especially with, you know, we've got a tin solder that's 95% tin. And so I have to be in that 240 to 260 degrees C temperature range. So now I have to look at the degradation of that material from an extraction standpoint and then be able to separate out that degraded soup of residue. So, you know, if I can't get it at 30 minutes and I have to stay at 40 minutes, I'll do that. But primarily, the faster is better, just so we can understand things that are going on. I actually have clients that will bring samples into my office. We'll extract them right in front of the client, run them through the IC system, and we're all just sitting there staring at the IC mass spec going, okay, I need data. But that's not a daily thing, so.
Terry, got a quick question for you. You
Thank
mentioned in passing that you've had changes in pH of the incoming samples, which can throw off your columns. You mentioned on the acidic side, do you have an issue on the basic side also? How much of an issue is this?
I'd say especially in the sodium and the ammonium elements, we get a lot of ammonium outgassing issues from some of the fluxes that are designed as water-soluble materials. And if they're overheated, the ammonium structure separates from that organic side, and we create a very corrosive ammonium element that is becoming a bigger issue as we move more people into the cleaning side. And there's a lot of cleaning chemistries using monoethanol amines as the cleaning chemistry. So we have an alkaline cleaning approach to neutralize the acid fluxes. So I get a blend of varying chemicals from my flux cleaning guys as well. Potassium is another problem too. So that's the other big element that we see is a potassium contamination from cleaning chemistries or etchants. So yeah, I'd love to see more detailed separation on the cations, because I think there's a lot more there going on than we understand.
Hey Terry, this is Ken.
If anyone else has a question?
Yeah. Hey Terry, can you hear me?
Yes, I can.
Yeah, very good presentation. Thanks for sharing your experiences. Um, I had a question related to the fluxes that you mentioned. Are the flux manufacturers doing any quality control?
A lot of their quality control is GC mass spec, but as a rule, no. They use blends and formulations that they've been able to develop over the years. Some of these blends came from the lab I was working in at Delco 30 years ago, 35 years ago. And, you know, adipic acid, malic acid, so whatever their source supplier is, they don't pay attention to the other elements that are in that activator. And again, you know, when you've got a solder paste that's 13% by weight flux, and probably a third of that is resin binding agent, you know, you get adipic, malic, glutaric, you start adding those in. But if you've got other materials, and that's one of the things that we found, that these flux vendors are not quality controlling their supplier base of the raw materials, and we get a lot of other very strange organics that start to pop up. And sometimes it helps, sometimes it just sits there and doesn't have any negative or positive impact, but it's now showing up as a detectable element, and that's where we actually are able to use the IC mass spec to, as a process control, looking at the raw material and say, look, you have these other ionics in here that are not being reported by your manufacturer of the fluxes. So, yeah, they don't, and I don't think they ever will, unfortunately. Until enough of us have IC mass spec, you know, in our labs, you know, at the Honeywells, at the guys at Raytheon, and you know, the large guys, GE Healthcare, you know, they're driving back the technology to the supplier base.
Okay, makes sense. Thank you.